Hello everyone. On this video we will be looking at finding the area between two curves or two functions. Alright, so to start that off, I want you to remember the concept of an integral. Okay, so this is our function, we'll call that f of x. That's the graph of f of x. If you remember, you have a rectangle here and there's a rectangle there. And the rectangles won't be symmetric because, of course, I'm doing it by hand, but hopefully you get the concept. And let's say you have a rectangle there and rectangle. You have rectangles all the way across. And all right, and let's say there. All right, now let's assume that the rectangles were drawn by someone with a steadier hand than what I have. If that's the case, then every single rectangle would have a width that we will call delta x. And each rectangle would have their own height that we will call f of x of I. Okay, now this one may be f of x of 1, this rectangle f of x of 2, this rectangle f of x of 3. In each case, your x of I is just a regular partition of A and B, where we know your I can equal 0, 1, 2, 3, all the way to some value n. Now, in some cases, your I could start at 1. That's no big deal. It can start at 0 or it can start at 1. It all depends. All right, so we know that if we add all of those rectangles up, our area is going to be approximately equal to, I'm going to give it a little bit of space here. That's the sum from I equals 0 or I equals 1 to n of f of x of I delta x. Okay, now remember, we're going to make those rectangles as small as we can. Okay, so let's say instead of having 50 rectangles, we'll get a more precise estimate if we have 100 or if we have 1,000 or if we have 1 billion. So in other words, the number of rectangles we wanted to increase because we get a more accurate value for the area. So we want to have that limit as n approaches infinity. Okay, and this is the area under a function to the x-axis. Okay, so from that function to the x-axis, this is our area formula. All right, now, I'm sure you've all seen this one right here. To find the area between the curves, it's really the same idea. Okay, so I'm not going to draw all the little rectangles because that'll take too long. But let's say we know that if we have the limit of the sum from I equals 1 to n of f of x of I delta x is the distance or the area from this function to the x-axis. So let's say this represents the area from that function to the x-axis. Okay, so what if we have another function g of x? If we want to find the area between those two functions or between those two graphs, we just have to get the function of f of x, or whichever function is larger or higher, minus the function of g of x. Because our g of x, that function will, I'll put that like a little slant, is from there to the x-axis. Okay, so if we wanted to find the actual limit in between these two, and we'll call that R for the region between f of x and g of x, we have the area under f of x, which we already know is the limit as n approaches infinity of the sum from I equals 1 to n of f of x of I delta x. And we have our area under g of x, which is equal to the limit as n approaches infinity of the sum from I equals 1 to n of g of x of I delta x. Now the area between the two that's going to equal the limit as n approaches infinity of the sum from I equals 1 to n of f of x of I minus g of x sub I delta x. But we already know that this is just equal to the integral from a to b of f of x sub I, f of x. Sorry, we don't need these sub I anymore. F of x minus g of x with respect to x. And this is what we will be using moving forward. You don't have to do all of this moving forward, just use that. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next page, which gives you really the general concept. There we go. So in general, what if we let f of x and g of x represent continuous functions where, just like on the previous page, f of x is greater than or equal to g of x throughout the entire interval of a and b. Okay, so I'm just going to cover this up for a quick second. Okay, so you notice here, everywhere for f of x is above every point for g of x between, let's say this is our a and this is our b. Now, that's not saying it won't cross further down the line, but between that interval, f of x is larger than g of x. Okay, so what if we let R, just like we did before, represent the region bounded above by the graph f of x and below by the graph of g of x, and bounded on the left and right by the lines x equals some number a and x equals some number b. Okay, so then the area of that region is given by a is equal to the integral from a to b of f of x minus g of x with respect to x. Now, there are some instances where f of x won't be larger than g of x. Your g of x may be larger than your f of x. So if that's the case, if your g of x is greater than your f of x throughout that interval, then a is equal to the integral from a to b, then g of x will go first. G of x minus f of x with respect to x. Okay. Now, on this video, we're just going to go over your linear functions. Okay, and it's going to be pretty simple, but on the second video, we're going to go over what happens when those videos cross each other in that interval. Okay, we're not going to do it on this video, but on the next one, we'll get a little more complicated and go through those steps. All right, so if you are still writing this, feel free to press pause. I know it's quite a little bit to jot down, but we're going to go ahead and move on to our first example. All right, so what if we let R, again, represent the region bounded above by the graph of the function f of x equals x plus 4 and below by g of x equals 3 minus x over 2 over the interval from 1 to 4. Find the area of that region. Okay, so here we have the graph. Okay, so we have f of x equals x plus 4 and g of x equals 3 minus x over 2, just kind of a quick sketch. Okay, and it's between x equals 1 and x equals 4. So really all we're looking for is this area. Okay, right in between there. Okay, so of course if you go from 1 to 5 your area will change, but we're just looking at 1 to 4. And of course that is called our region R. Okay, so that's what we're solving for. Okay, now just a quick note. The point of intersection is not in the interval. One, 4. Okay, now that doesn't mean much for this particular problem, but moving forward, that is very important, a little very important detail that you're going to want to look for moving forward. Okay, like I said, on this one, it's not in the interval, so it doesn't make a difference, but definitely is something we want to pay attention to. Okay, so what do we notice between that interval? That every value of f of x is larger than the value of g of x in that interval. Okay, so since f of x is greater than or equal to g of x for the entire interval from 1 to 4, we're going to use the formula a is equal to the integral from a to b. Since f of x is larger, we go f of x minus g of x with respect to x. Okay, now in this case, your a is equal to 1 and your b is equal to 4. So that's going to equal the integral from 1 to 4 of your f of x, remember that's x plus 4, minus your g of x, which is 3 minus x over 2 with respect to x. Oh, all right, let me move that up. Okay, now here we're going to combine our like terms, so I'll do that over on the side. So x plus 4 minus 3 minus x over 2, that gives us x plus 4 minus 3 plus x over 2 once we distribute our minus sign. Okay, so if we make this x 2x over 2 and add it to this x over 2, that gives us 3x over 2, and 4 minus 3 is plus 1. So this becomes the integral from 1 to 4 of 3x over 2 plus 1 with respect to x. Okay, so now that we've combined those, we can go ahead and integrate. You can integrate here if you wanted to, but it will be very complicated moving forward. So you want to simplify what's in here first and then integrate. Okay, so if we integrate 3x over 2, that's going to equal 3x squared over 4. Move that up. Plus, the integral of 1 is just x. And that's from 1 to 4. Okay, so from here, we're going to go ahead and use the fundamental theorem. So we're going to plug in our 4. So 3 times 4 squared over 4 plus 4 minus, now we plug in our 1, 3 times 1 squared over 4 plus 1. Uh-oh, there you go. Okay, so this will end up being 16 minus, that's going to be 7 over 4. So if we rewrite that, this will be 64 over 4 minus 7 over 4, which is 57 over 4 square units. And this is your area of your region. Move that over a little. There we go. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example, which we're going to show how to find your point of intersection if you don't have a graph. All right, so if you're still writing, feel free to press pause, but we're going to go ahead and move on. All right, so what if you wanted to calculate the area bounded by g of x equals 4x plus 5 and f of x equals 5x plus 8 over the interval -14 to -8? Okay, so to find the point of intersection, without a graph, make f of x equal g of x and solve for x. Okay, so your first step, find the point of intersection. Okay, so f of x equals g of x, meaning we have 4x plus 5 equals 5x plus 8. Clean that up. Okay, so if we subtract 5x from both sides, you get negative x. If we subtract 8 from both sides, you get minus 3 equals 0. So in other words, x equals negative 3. All right, so we have a quick little number line just to kind of see where it is. That's your negative 14, that's your negative 8. So your negative 3 will be somewhere over here. Okay, so this is to the right of the interval. It did not fall in between there. Okay. Now, since we know that that's not inside the interval, we can go ahead and just see which one is larger, the f of x or the g of x. Again, assuming we don't have a graph. So to find which function is larger in the interval, pick a test point. Okay, so you want to pick a test point inside of there and just plug that value in both your g of x and f of x and see which one's bigger. That's it. So I'll get the test point x equals negative 9. Again, you could pick negative 10, you could pick negative 13, you could pick negative 13.9. It does not matter. I just picked 9 just because it was completely random. And you plug that value into your f of x and g of x. Okay, so f of negative 9 is going to equal 5 times negative 9 plus 8, which is negative 31, or negative 37. And g of negative 9 is 4 times negative 9 plus 5, which is negative 31. Okay. Well, what do we know? Well, we know that negative 31 is greater than or equal to negative 37. So that means, in this case, g of x is greater than or equal to f of x for this interval. Okay. And if you're ever confused about that, just draw your number line. You have, let's say, negative 37 here, negative 31 here. And let's say you go down to 0, you have 1, and you have 2. Pick any numbers. So if you notice, the number to the right is larger. So 2 is bigger than 1. So negative 31 is bigger than negative 37. Like I said, if you're ever confused, just draw the number line, and it'll help you kind of figure it out. All right, so since we know that g of x is greater than or equal to f of x in our interval, our area is going to equal the integral from a to b of g of x minus f of x with respect to x. Okay, so whichever function is largest in that interval goes first. Okay, so that's going to equal, remember your a and b is negative 14 and 8. So from the integral from negative 14 to, well, negative 8, sorry about that, of your g of x, which is 4x plus 5, minus your f of x, 5x plus 8, with respect to x. Okay, and again, we combine our like terms and everything, so we simplify what's in there. So that gives us the integral from negative 14 to negative 8 of negative x minus 3 with respect to x. Then we go ahead and we integrate. Okay, so the integral of negative x is negative x squared over 2 minus the integral of 3, which is 3x. And that's from negative 14 to negative 8. So we go ahead and we use our fundamental theorem. So we plug in our negative 8. So we have negative 8 squared over 2 minus 3 times negative 8 minus, now we plug in our negative 14, or negative 14 over 2 minus 3 times negative 14. Okay, so 64 divided by 2, negative of that will be, so that's negative 64, negative 32 plus 24 minus, oh, I forgot my square there, negative 98 plus 42. So that's going to equal 48 square units as our area. All right. So remember, first thing you want to do is find your point of intersection. And then if it's not in the interval, you just pick a test value in that interval to find out if your f of x or your g of x is larger. And then you put the larger function first. All right. So if you are, oh, let me push that back up in case you're still writing. So if you are still writing, feel free to press pause and finish up. But we're going to go ahead and move on to our next example. All right, so what I want you to do is go ahead and find the area bounded by f of x equals 2x minus 1 and g of x is equal to 7 minus 3x. And they're bounded horizontally by x equals negative 2 and x equals 0. So what I want you to do is go ahead and press pause and try to do this one on your own. Alright, so I'm assuming you've pressed pause and worked this one out. So let's go ahead and verify your answer. Okay, so first thing we want to do is find our point of intersection. Okay, so we do that by making f of x equal g of x. Okay, so that means you have 2x minus 1 equals 7 minus 3x. Okay, so if we add 3x to both sides, we get 5x. If we subtract 7 from both sides, we get minus 8 equals 0. So if we add 8 to both sides and divide by 5, we get x equals 8 over 5, which is 1 3/5. Okay, so 1 3/5 is not in our interval. Okay, so you have your -2, you have your 0, your 1 3/5 is going to be about right there, which we don't have to worry about. All right. So now we go ahead and plug in our test values. So between 0 and -2, let's say you pick x equals -1 as your test value. Okay, so f of -1 equals 2 times -1 minus 1. So -2 minus 1 is -3. And g of -1 is equal to 7 minus 3 times -1. -3 times -1 is +3. 7 plus 3 is 10. So we see here that g of x is greater than or equal to f of x for the entire interval of -2 to 0. Okay, so what does that tell us? Well, that tells us g of x goes first. So our area is going to equal the integral from a to b of g of x minus f of x with respect to x. Okay, so remember your a is -2, your b is 0. So you integral from -2 to 0, 7x minus 3 minus 2x minus 1 with respect to x. Let me clean up that 3 a little bit. There we go. Okay, so we go ahead and we simplify what's in there, combine our like terms and all that good stuff. So we end up with the integral from -2 to 0. 7 minus 2 is 5. So we have, oh, did I put that wrong? Yep, I did put that wrong. That's why it's good to double check. So yeah, f of x, this should be 2x. Oh, no, I didn't. Yep, 7x minus 3. 7 minus 3x, that's where, okay. 7 minus 3x. I'm like, something did not look right. There we go. Alright, so I'll put 7x minus 3 should be 7 minus 3x. Okay, so minus 3x minus 2x, that gives us -5x. There we go. Okay, now things are looking better. Okay, and 7 minus negative, so 7 plus 1 is 8. -5x plus 8 with respect to x. Okay, need to slow down. I'm jumping ahead too far. Okay, so that equals Well, actually, we don't need this because we're going to go ahead and just integrate. There we go. So if we integrate negative 5x, that's going to be negative 5 over 2x squared. And if we integrate 8, that's just going to be 8x. And that's from negative 2 to 0. All right. So we go ahead and do our fundamental theorem. We plug in our 0. We can just know that's going to be 0, but we'll go ahead and go through all the steps. So negative 5 over 2 times 0 squared plus 8 times 0 minus negative 5 over 2 times negative 2 squared plus 8 times negative 2. Again, 0 and 0, that's just going to be 0, so that whole thing just disappears. Here you have 4, so you have negative 4, well, positive 4 times 5, so you have negative 20 over 2 plus, minus 16. So that'll be minus 16, but if you distribute, actually that becomes plus, so that's plus, and that's plus 16, which is equal to 20 over 2, and that's 16. We can make that 32 over 2, which is 52 over 2, which is equal to 26 square units as the area of our region. Okay, so it's not too bad. It's pretty straightforward. Okay, again, it takes a little bit of practice. All right, so again, like I said, we did mostly linear problems here. We're going to move over to quadratic and cubic problems in the next video, but I want you to understand the basics before we get a little more complicated. Okay, so hopefully this made sense, and I will see you on the next video.